Once we place those cameras into position, we then need to calibrate them. So how does the system know where each camera is in relation to one another? So we call that process calibration. And what we do is we move around the space with a wand, basically calling like Dolphin dance. And that is primarily used to triangulate the position of each cameras in 3D space. Once we defined that positioning of the cameras, we then need to define where our floor plane is, essentially. So we need to tell the system where is the ground, where do we stand, basically, where does it live. And we do that using a ground plane, which also is used to define our forward and left and right direction axis, so that when we take that data and use it in 3D applications, we can marry those worlds up together and we won't have any offsets as such. Before we start calibrating our system, we need to make sure that there are absolutely no retroreflective material within our volume. Because what that may do is it might consider any sort of metallic surface or any interference as a marker itself. And that could essentially be a problem when we capture our data later on. So the first thing before we start calibrating is to make sure our volume is completely clear and there are no more hidden markers in the space. So this is the one we're going to use to calibrate our system. Essentially what we're going to do is wave this in a dolphin-like figure-8 figure inside the volume. And essentially what this is going to do is, with these predefined marker locations, it's going to tell our cameras exactly where they are in relation to one another. So the last step in our calibration process is to define where the floor is, and that is using one of our OptiTrack ground planes right here. The longer end of the object is which we're going to use to tell us which way our forward direction is, and smaller length of the object is which way is going to be our left and right direction. So now Dan is doing our dolphin dance in the volume, which is waving the calibration wand in a figure-8 manner. And what he's essentially doing is walking in a grid pattern up and down to make sure we have enough coverage from all the cameras to see the wand. And we can see here with these lovely colors what our coverage really means. Now we are looking for general coverage throughout most of the cameras so that we know that we can evenly track markers throughout the space, basically. And once we are happy with a specific value count, we can then hit apply and the computer will calculate all those samples. So essentially the balance of our coverage and our number of samples captured by our system will generate a value in millimeters, which essentially, when we're using optical systems, we're generally looking for below 0.5 in error.